All right, at the end of the last video, we set ourselves the task to implement the following function, that given our example table and starting from a particular integer, we would like to perform 3 successive lookups in this table, meaning that whenever a lookup yields a number, we use that number that we just received as the input for the next lookup. Then if these 3 lookups all succeed, then we return the final result incremented by 1, so the result of the third lookup. And if any of the lookups fail, then the whole operation should fail. Okay, so let's try to just do this. I'm going to call this function 3lookups, and it takes this initial integer, and the result is going to be a maybe int. Right? We get an int back in the successful result, but we want to have the option to fail, so it should be a maybe of integers. And we're going to just use the example table here. Let's actually call it table rather than example. We're going to use this as a constant in the function. I could easily parameterize 3 lookups over the table that we're using as well, but it doesn't add anything here for the example. So let's just do it like this, okay? So we start with our initial integer, we give it a name, and I'm going to call it I0 for reasons that will hopefully become obvious in a moment. And the first thing we want to do is we want to perform a lookup in our table. So I'm going to do m lookup of I0 in our table. And at this point, the function actually type checks, so I could load it and I could do 3 lookups on 4 and I get just 8. So it actually type checks, but it of course does not actually do what we want it to do, because we wanted to perform 3 lookups, and we want it to perform this logic that if any of the lookups fail, the whole operation should fail. So here we now need to do 2 things. We need to check whether the lookup failed for 2 reasons. For once, well, if the lookup failed, we want to fail the whole thing. But the other reason is because we want to have the successful result, if it then exists, as an input for the next lookup. So we're going to do a case distinction here on the result of the first lookup. And we have 2 cases to consider. One, that the lookup fails. I'm going to put a hole here. And one, that the lookup succeeds. Now, if the lookup fails, then we are in this situation here. If any of the lookups fail, then the whole operation should fail. So if we get nothing, then we produce nothing. So that looks a little bit strange, but it does make sense. And like if the first lookup results in nothing, then nothing is actually the final result of this function, and we don't do anything anymore. At this point, we're done, whereas here, we're still going on. Here we now have I1, and we're essentially doing the same thing again. We're doing another lookup, but again, we have to look at the result of the lookup. And again, we have to distinguish the case where the lookup fails or the lookup succeeds. All right. Now, again, if the second lookup fails, we're going to return nothing. If the second lookup succeeds, then we're having a new integer. That's the result of the second lookup, and we want to perform a third. So I'm going to do the same thing again. So we're going to look up I2 in the table. And again, we're going to have 2 cases to consider, namely the one where the lookup fails and the one where the lookup succeeds. Perhaps to make it look even more symmetric, I should actually change the indentation a little bit. Right. And now, if the third lookup fails, we're still planning to fail the whole thing. But if the third lookup succeeds, then we are finally in this part here. If all the lookups succeed, then we return the final result incremented by 1. So the final result is I3, and we return that one incremented by 1, so we return I3 plus 1. Let's try our function now. It type checks now. And if we do 3 lookups based on, say, the number 2, then we get 17. And this is why I said we are keeping our example table relatively systematic, so that we can, without going back to the example table, see that this is reasonable, because it always doubles. So 2 goes to 4, 4 goes to 8, 8 goes to 16, 16 plus 1 is 17. So that's fine. So the only question is, are all the results contained in the table? So if we do start with something that is not contained in the table, then we get nothing. If we start with 4, for example, it still works, because 4 goes to 8, 8 goes to 16, 16 goes to 32, and all these were still in the table, and then we get to 33 as the final result. Right? If we start with 5, it actually also works, because 5 goes to 10, 10 goes to 20, 20 goes to 40, all these are in the table, and then 41. But if we, for example, start with 16, then the first lookup still succeeds, because 16 goes to 32, and 32 goes to 64, but then the third lookup fails, and then we end up with nothing. So this looks fine. This looks like it actually implements what we wanted to implement. And it is relatively straightforward, I would argue, in the sense that we have performed the 3 lookups, and we have been implementing this notion that if any of the lookups fail. But it is nevertheless an unsatisfactory solution, I would say. It is not very nice. There is a lot of noise here. In fact, the whole definition is dominated by this logic of analyzing the results of the lookups, whether they are successful or not. There are 3 separate lines, line 34, line 37, line 40, for this notion that if a lookup fails, then we fail. None of these lines say anything but that, right? And even the whole case is basically just there for that. And if you look at the way that we've described it up here, we made it more of an afterthought in the specification. We said, oh yeah, and by the way, if any of the lookups fail, then the whole operation should fail, right? It doesn't clutter up our main part of the definition. But here, it's sort of dominating. In fact, if we want to see what the function is really doing, that it is performing 3 lookups, right? We have to look closely and zoom in quite a bit, and then that it adds 1. These are the interesting things that are happening, but they make up only a small part of the overall definition. So that is what is not so nice here. Now, we could be trying in this particular case to somehow make it more regular, right? I mean, because we have 3 lookups, it might actually make sense to generalize and say, let's write a function that does n successive lookups and have a function that is parameterized by a counter and then calls itself recursively. And then we would perhaps not have to have 3 nested case expressions, but rather would get some recursion on an integer. And that is one good approach that works in this case. But it works because in this particular case, what we're doing is actually very uniform. We are actually performing 3 successive lookups. In other APIs using maybe results, we may actually really want to do 3 different things, 3 specific different actions in sequence on the previous result, each of which can still fail, but all the 3 actions are actually different in nature, and we would still get this sort of nested case expression as a result, which is kind of dominating and cluttering up the entire logic of what we really want to express. So it might be more interesting to explore if we cannot abstract from this recurring pattern, from the recurring pattern directly. And that is essentially these 3 lines, all right, they repeat more or less, apart from minor differences, 3 times here. Right? Perhaps I'll put this one onto the final line as well to make it even more clear that lines 33 to 35 and are very similar in nature to 36 to 38, which are very similar in nature to 39 to 41. And if you remember what we have been doing in the context of deriving the fold functions, the fold R and the fold L prime functions, we have essentially been looking at a number of similar programs, and we have been extracting the commonalities, and we have been coming up with a new function, these fold functions, that capture the recurring patterns in these functions. Here we have a single function that has a recurring pattern. We can still try to do the same thing. Right? We can try to abstract from this pattern. As usual, when we abstract from a pattern, we don't really know what's coming out of it, so a good name is difficult to invent in advance. So let's just call it fun for function again. And let's just see what we want to capture. We want to capture this idea that we have a case of some computation. Now, in this particular situation, all these computations are lookups. So I could actually say, I want to capture the fact that I'm doing a particular lookup in my table, right? But as I've just been trying to argue, that's perhaps too specific. In a different scenario where I'm interacting with a different API, I may not actually want to perform lookups. The essence of this example is that I'm performing some computation that has a maybe result. So let's just abstract from this entire computation that may have a maybe result here. So I want to check whether a particular computation that I'm calling comp now is either nothing or just of something, right? And because I'm abstracting over the computation, I now also don't necessarily know that it will result in an integer, so I'm not calling the result just I, but I'm calling it just x, because it can in principle be anything. But now, one thing that I do want to keep abstracting over is this notion that if something fails, then the overall thing fails. So I do want to make it a part of the pattern that I'm abstracting from that nothing maps to nothing. Right? So as soon as we hit something that fails, we fail. And now, here, what goes here is always different, actually. That's a little bit interesting to see, because we don't have any content. The way I've now layouted this, we don't have any content here to the right-hand side. But to the right-hand side of this arrow in the just case is always the entire rest of the computation. So in the case of the first three lines, right, what comes after this just is the entire rest here, from here to here. And in the case of the second case expression, what comes after this right arrow in the just case is still the entire rest of the computation. And after the third one, it's still the entire rest of the computation. All right, so that is always different. So we do give a name to this part of the computation as well, because it's not always the same. But it's important that we can use the x in this rest of the computation. So so we should make that a parameter of this rest of the computation that we have here. Let's call it rest, and we are going to apply rest to x to make it clear that the rest can use the x, because we're using I1 in the rest of the computation, we're using the I2 in the rest of the computation, and we're using the I3 in the rest of the computation. So we always do this. All right, so now we have actually abstracted from the pattern that occurs here 3 times over. We have given names to the things that are variable, right? So the expression that appears within the case of phrase and the rest of the computation, which can use the successful result. Now that we've given names to them, they're currently not in scope, but we do the same thing that we also did when we derived the fold functions. We're going to make these arguments of our function that we are just being defining. And then suddenly the function type checks, and it is inferred to be of this type. And actually, let me change the variable name so that I'm renaming t to a and a to b. And then we see that what we're doing here, we're combining 2 possibly failing computations into a new possibly failing computation. So we start out with a maybe of A, and then we have a maybe of B, and we combine them into a maybe of B, only that additionally the second computation gets access to the successful result of the first one, if it then has been successful, right? And if any of the two computations fail, then the overall thing fails, right? Explicit in the definition is only that if the first one fails, the overall thing fails. But obviously also, if the rest of X evaluates to nothing, then that is the end result of the computation as well, right? So really, if either of the two component computations result in nothing, then the end result is nothing. Only if they both succeed, the end result will be a successful result. Right? Now, this type signature is perhaps familiar to you if you think back about what we've already been covering in this course. We have very recently been encountering a very similar type signature in a slightly different context. Perhaps you can remember this on your own, so I'm going to slow down for a bit, wait a few more seconds. You can perhaps pause the video and think about it. The right answer is bind. In the context of I/O, we have seen that there is this bind operation, which is of type IOA to A of IOB to IOB. You can see if you compare fun and bind, the only difference is that here we mention maybe, where bind mentions I/O. And I/O was a sequencing operation on I/O actions, right? Bind was a sequencing operation on I/O actions. And if you think about it, fun, you can see fun as a sequencing operation on maybe computations as well, right? We're doing one possibly failing thing and then another possibly failing thing, and we're combining these two things together into a single possible failing thing, and the second possibly failing thing, that is this part, can make use of the result of the first if it then happens not to fail. And additionally, we have this failure propagation semantics in here. So perhaps inspired by the similarity of the new function that we have been discovering here and the bind operator on I/O, let's give this one a similar name. Let me just use a bind but with 3 greater than operators. And then we can also write it infix if we want, between the computation and the rest. And now we've just been giving it a different name. All right. And we can also call it bind for the time being. So what remains now is the task to actually use this operation in our 3lookups function. So let's try to do this. Now, this is lining up essentially the body of the definition here with what we have here and seeing what need to become the arguments of our bind operator. So comp is the stuff that is between the case and the off. That is going to be the first argument of our first invocation of bind. And now we don't need the nothing arrow at nothing because it's part of the definition of bind, and we don't need the just I1 either. But what we do need to put here is a function rest, all right, that takes the successful result. So here we can say lambda I1, and then uses it in all the rest of the computation, which should still have maybe type. And look, at this point, we have been replacing the first 3 lines, the first case, with a lookup. Right? So perhaps I should actually go back once more, right? So what we had before, that was this. And perhaps we should actually make a copy so that we have the old and the new version side by side in the end. We can see where we started out and where we ended up. So let's call this one 3 lookups original, and this one 3 lookups. And then let me repeat what I just did here. Here we made the call to lookup the first argument to our bind, and then we wrote lambda I1, and then we could get rid of these 2 lines. And at this point, the function still type checks. And actually, it's 3 lookups is the name of the new function now. It still behaves as before. On 4, it returns just 33. On 16, it returns nothing. And now we can do the same thing again. We can replace the second call here also. So m lookup I1 table becomes the first argument of our second invocation of bind. And then we get a lambda term that picks up the I2, which is the successful result, and we can get rid of these 2 lines. And then we can do it again, m lookup I3 of table, bind lambda I3 arrow, and we can get rid of these 3 lines. And now if I reload, I2 of table. Right. And now if I reload and try this, it still works. And now if I perhaps even realign this to look like this, I would argue that we have a function definition, if we compare this with what we started out with, that is much nicer. Right? Because now if you look at what is highlighted here, we are highlighting the actually interesting parts. We're saying we're doing a lookup of I0 in the table, and then we call the result I1, then we look up I1 in the table again, and we call the result I2, then we look up I2 in the table again, we call the result I3, and we finally return I3 plus 1. That is exactly sort of the successful path, right, that we're focusing on here now. Right? And the fact that, oh, by the way, if any of the operations fail, then the whole thing fails. That is still clear, but it is not dominating. Why is it clear? Well, because we still have a maybe result type of the overall computation, and we still have a definition of this bind operator, and this bind operator captures exactly this notion. Oh, by the way, if any of the constituent operations fail, then the whole thing should fail. Right? But it is hidden away in the bind now. That is capturing exactly this desired failure propagation semantics. It's no longer dominating and cluttering up our entire definition. The definition can now focus on the parts that are interesting. Right? So that is a useful abstraction. And that's a useful intermediate result already. Right? But we have seen that the bind operator that we have been defining here has similarity to the bind operator that we have been discovering in the context of I/O. And perhaps inspired by that, we can discover even more similarities. And perhaps we can make the definition yet slightly more nice, right? Yet slightly more concise and beautiful. And we'll discuss that next.